Hello and welcome to lesson number 33, Complex Numbers Part 3. In the previous videos, lesson 31 and 32, links in the top right and in the description, we talked about what complex numbers are, how they work, how to do arithmetic with complex numbers, and we also talked about two special operations on complex numbers, taking the modulus and taking the complex conjugate and identities related to them. Now in this video, we're going to be talking about how we can geometrically represent a complex number. To start off, before we can geometrically represent a complex number, we need to find out a proper geometrical representation system that we can use to do so. So considering a complex number, any complex number say z can be written as a plus bi, where a and b are two real numbers. So we can say a comma b are elements of the real number. So we can see any complex number z can be written as a, which is a real number, plus b, which is a real number, times I, which is the imaginary unit, and the combination of these two will create a complex number. Now considering this complex number, since a can be any real number, a has a real degree of freedom. And similarly, since b can also be any real number, b also has a real degree of freedom. Now considering that, if we take a look at the overall complex number z equals a plus bi, since a and b both each have a real degree of freedom, the overall complex number z, which is a plus bi, has two real degrees of freedom. Due to this, when we geometrically represent a complex number, we do so on a two-dimensional plot like this. As you can see here, I've drawn a two-dimensional set of axes here, but these axes are not the axes of the xy plane. Instead, when we draw the axes to represent a complex number, we label the x-axis direction as the real axis and call it RE, and then we label the y-axis direction as IM for the imaginary part. And then this kind of diagram is called an Argand diagram. So in this diagram, we can see we have a real axis and we have an imaginary axis. Now the intersection point of these two is this point right here, which is called the origin and is representative of the number 0, since the number 0 is the only number with real part 0 and imaginary part 0. Now considering that, any other number can be represented on this axis plane here by simply considering the real part and imaginary parts of the number. So if we consider the complex number z, we can see z has real part of a and imaginary part of b. We don't say it has imaginary part of bi because the I is implied in the imaginary part, so we just take the b. Now given that, let's suppose that a and b are positive for our example, because if they're negative or they can be negative, then we cannot really plot it easily. But if we assume they are both positive, then we can plot z on this complex plane here, the Argand diagram that we have here, by simply considering the real part a and imaginary part b. So on this axis plane, what we'll do is to start at the origin and then we're going to move rightward a distance of a. So doing so, if we go like this until we reach the point A here, we can stop and say that the real part of our complex number z is the part A. And then for the imaginary part, which is b times I, we have b as the coefficient of the imaginary unit, and then what we have to do is to go in the imaginary axis direction a distance of b. So considering that, if we go to this point, now from this point we can go upward along the imaginary axis a distance of b. Again, if b was negative, we would be going downward. So going upward a distance of b like this, we can see if this point right here is representative of b, then matching this and this together, we can see we reach a point here, and this point right here is the point representative of the complex number z. So the complex number z, which is equal to a plus bi, can be represented on the Argand diagram by moving a distance of a along the real direction and a distance of b along the imaginary direction. Now of course, if a was negative, then we'd be somewhere over here, and if b was negative, we'd be somewhere over here. But other than that, okay, you can see I represented a general point z, which is a plus bi, using the Argand diagram like this. So we can do this for any point. We can do this for any point that we want. Considering a couple of examples, if I go down here, let's say we want 3 plus I. 3 plus I can be represented by going a distance of 3 along the real axis and a distance of 1 along the imaginary axis, since we have I here, which is 1 times I. So therefore, if we go 3 here, and then we go, let's say 1 is about this much over here, we're going to get to this point right here, and this point is representative of the complex number 3 plus I. Now let's say we go in different direction and we do, let's say, 2 minus 4i. Then to do 2 minus 4i, we have to go 2 in the positive direction in the real axis, which is going to be over about here, and then we need to go minus 4 distance in the direction of the imaginary axis. Now since the positive direction is upward, we're going to have to go in a negative direction, which is downward. We're going to have to go a distance of 4, which means we are going to be somewhere over here, negative 4. And then adjoining these two, if this is 2 and this is negative 4, then this point right here is representative of the complex number 2 minus 4i. Now if we do another one, let's say minus 1 minus 3i, minus 1 minus 3, actually let's not do that example, let's do minus 1 minus 2i. So for minus 1 minus 2i, on the real axis we can see the real part of this complex number is minus 1, so we need to go 1 in the negative direction, which if the positive direction is rightward, the negative direction is leftward, so somewhere over here. Here we have minus 1, and then we need to go to minus 2 in the imaginary direction, which is going to be right over here, minus 2, and therefore the complex number represented here is minus 2 and minus 2, minus 1 and minus 2i, which is this point right here. Now you can see when you represent these, if the real part is positive, we are on this side. If the real part is negative, we are on this side. And similarly, if the imaginary part is positive, we are above the line like this, and if the imaginary part is negative, we are below the line like this. Now with this, we can get 4 combinations: imaginary and real both positive, imaginary and real both negative, imaginary positive real negative, and real positive imaginary negative. These 4 make 4 different quadrants in this plane. So in any Argand diagram, you will have 4 quadrants similar to how you have 4 quadrants in the xy plane, but in this, the 4 quadrants are this quadrant right here, this quadrant, and this quadrant. In the first quadrant, both the real and imaginary parts are positive. In the second quadrant, the real part is negative but the imaginary part is positive. In the third quadrant, both the real and imaginary parts are both negative. And the fourth quadrant, only the real part is positive and the imaginary part is negative. Now, in trigonometry, you know that these 4 quadrants are related to the signs of the trigonometric functions sine, cosine, and tangent. In the first quadrant, all of them are positive. In the second quadrant, only the sine value is positive. In the third quadrant, only the tan value is positive. And in the fourth quadrant, only the cosine value is positive. Now, this is actually related to the complex numbers also having everything positive here, the real part being negative here, but imaginary part being positive, both real and imaginary being negative here, and here only the real part being positive. But we will see that connection a little bit ahead in this video, but for now I want you to note that there is some interesting geometrical connection in between the complex number signs in the Argand diagram and the sine, cosine, and tangents of angles as we go around in the 4 quadrants in trigonometry. So now let's take a look at how this geometrical representation can be converted into trigonometric form and how we can establish the connection between sine, cosine, tan signs, as in the positive or negativeness of sine, cosine, and tangent of different angles, and the 4 quadrants in the Argand diagram. Now before we do that, let's first take a look at what different algebraic operations look like on this new geometrical representation. So going down, the first thing we're going to consider is multiplying a complex number z by a scalar or real number lambda. So what I'm going to do is to draw the real axis like this and the imaginary axis like this, and then we're going to consider complex number z, and then we're going to consider z equals a plus bi and consider multiplying z by a real number as lambda z and consider what that's going to be equal to. So now here we can see directly, if z is equal to a plus bi, then lambda z must be equal to lambda a plus bi. And we can see if we expand the brackets out, we're going to get lambda a plus lambda bi. Now, considering the real and imaginary components here, the real component of lambda z is lambda a and the imaginary component is lambda b. Now, if we consider the point z, and let's suppose the point z is this point right here, which is going to be z equals a plus bi, we can see for the point z, if we draw a line from the origin to that point like this, and if we consider the angles and the lengths involved, considering this angle and drawing this line right here, the vertical height here is b based on our definition, and the horizontal length here is a based on our definition. Now, considering the angle here, we can see the tangent of the angle is equal to b divided by a. Now after this, if we consider the second point, which is lambda times z, we can see we have lambda a plus lambda bi. Now considering that point, we can see if we divide the y coordinate here by the x coordinate, or the imaginary component by the real component, we are going to get lambda b divided by lambda a, which is again going to be equal to b divided by a. Now therefore we can say the tangent of the angle here corresponding to the point lambda z is going to be equal to the tangent of the angle corresponding to the point z. And therefore the two angles are going to be similar. So due to this, we can say that the point lambda z is also going to be along the line that goes from the origin to the point z. So if we extend this line like this and we extend it in the reverse direction like this, then we can say that the point lambda z is going to be somewhere along this line. Now where exactly it is along the line depends entirely on the value of lambda. If lambda is equal to 1, then of course the point lambda z is going to be exactly at the point corresponding to z. But then if lambda is greater than 1, and if it's in between 0 and 1, if it's negative and in between negative 1 and 0, and if it's less than negative 1 rather, there are different things that happen. So considering the first case, if lambda is greater than 1, it means the distance from origin to the point of lambda z is going to be greater than the distance from the origin to the point z. And it also means that lambda z is going to be in the direction of z. Now due to this, we can say that if lambda is greater than 1, then lambda z is going to be somewhere over here. So all of this, all the way up to infinity on this side of the line, is going to be correspondent to lambda greater than 1. Now after that, considering lambda in between 0 and 1, if lambda is in between 0 and 1, it means that lambda z is going to be a smaller number than z. And due to that, the distance of the complex numbers lambda z from the origin compared to the number lambda is going to be smaller. So because of this, we can say if lambda is in between 0 and 1, lambda z is going to be along this line right here. So this is the case where lambda is in between 0 and 1. And the reason we say in between 0 and 1 is because if it is equal to 0, it is going to collapse slowly and slowly downward until lambda times a is approximately equal to 0, since lambda is approximately equal to 0, and lambda times b is also approximately equal to 0. Now we can see as lambda approaches 0, this point is going to end up going closer and closer towards the origin, and in fact in the limit it is going to be equal to the origin. So ignoring that case, if we just say lambda in between 0 and 1, then lambda is going to be somewhere along this line right here. Now, similarly, if we consider the negative case, if we multiply lambda by negative 1, if we multiply z by negative 1 or take lambda is equal to negative 1, we're going to get the point that is completely mirrored across the origin from the original point z. So right here we're going to get negative z, which is equal to negative a minus bi. So therefore this point right here is negative z. Now considering that if lambda is somewhere in between 0 and negative 1, then we are going to be somewhere in between the origin and this point right here. So therefore if lambda is in between negative 1 and 0, we're going to be along this line. So we can say for lambdas greater than negative 1 and less than 0, we're going to be along this line. Now after that point, if lambda is a greater negative number than negative 1, or we could say lambda is less than negative 1, then we're going to be along this line right here, and this line extends all the way to infinity, similar to the line on this side. So we can say if we're along this thing, then lambda is less than negative 1. And that is the full diagram of all of the different scalar multiples of lambda times z. If we have lambda times z where lambda is greater than 1, we're going to be in this direction. If we have lambda times z where lambda is in between 0 and 1, we're going to be like this, where this is the original point z. If we have a negative lambda, and negative lambda is between negative 1 and 0, we're going to be like this, where this is the point corresponding to negative z. And if lambda is something greater than, or rather I should say less than negative 1, or we can say a greater negative number than negative 1, then we can see we're going to be in this direction right here towards infinity, past the point corresponding to negative z. And that is the summary of all scalar multiples of a complex number z. Now after this, the next thing we have to talk about is taking the complex conjugate. Now taking the complex conjugate is actually quite simple compared to multiplying by a scalar, because if you consider any random number, let's say this number right here, which is z equals a plus bi, z conjugate is just a minus bi. So we can see we keep the real part constant, but we make the imaginary part negative. So due to this, if the real part is along the x-axis like this, the real axis, and the imaginary part is along the y-axis or upward axis like this, then if this is the positive imaginary part rather of b, then the negative part is going to be negative b, meaning that z conjugate is just going to be the exact same point z mirrored along the real axis. So therefore, we go the same distance along the real axis, but then instead of going one direction, we go in the inverse direction for z conjugate. So therefore, we can see we have a perfectly mirrored point where this distance is b, this distance is also b, but while this b is in one direction, this b is in the inverse direction. So we can see the point here is upward like this, where this is some certain angle, let's say alpha, and then the other point here is exactly mirrored, and due to that its angle here is also alpha, but instead of being on one side of the real axis, it's on the inverse side. So this point right down here is what we're going to mark as z conjugate. Now this of course also works for points over here. If you have a point over here, it's going to be mirrored and it's going to be corresponding to a point over here, which is the conjugate, and so on. So any conjugate of any complex number is just going to be that number mirrored across the real axis. Now after this, the final thing we have to consider is how we can geometrically represent addition and subtraction on this kind of Argand diagram. Now that's also quite easy to do, so I'm going to consider an imaginary axis here and the real axis here, and I'm going to consider two complex numbers, let's say z1, which is going to be equal to a1 plus b1i, and another complex number z2, which is going to be equal to a2 plus b2i. Now, if we consider these two complex numbers, let's suppose that the first complex number is somewhere over here and the second complex number is somewhere over here, just for the sake of supposing. So we'll call this one a1 plus b1i and this one a2 plus b2i. Now, if you consider adding these two, we can see when adding the two complex numbers, the complex numbers can be broken into real parts and imaginary parts, and the two real parts of these two can be added together, and the two complex or imaginary parts can be added together separately. So doing so, z1 plus z2 can be written as a1 plus a2 as the real part plus b1 plus b2 times I as the imaginary part. Now considering this, we can see the real part is a1 plus a2, meaning to get to this point, we need to go the distance a1 and then also go the distance a2 in the horizontal direction along the real axis. And then similarly, since the vertical component or the imaginary part is b1 plus b2, we need to go the vertical distance b1 and then also go the vertical distance b2. So therefore, we need to add both distances of both points in order to get to the final point. Now note, if we do the components of the first number, first let's say we do a1 and b1 in this direction and this direction respectively first, we're going to end up at the point corresponding to z1. And then if we add to that a2 and b2, it's basically going from the point corresponding to z1 a distance of a2 like this and a distance of b2 like this. So we can think we're basically moving the origin from where the origin is supposed to be to the point corresponding to z1 and then drawing the complex number z2 starting from the point z1. So we can see if we represent these as vectors, then we can basically just consider the two complex numbers to be two complex vectors that send you from one point to another point, and then we can see adding two complex numbers together is basically the same as vector addition, because if you take this vector right here and move its base to the end of the first vector, we can see we're creating the final complex number, which is this complex number right here, which is basically the vector sum of the two original complex numbers. So by this we can see when you add two complex numbers together, you're basically thinking of these two complex numbers as two different vectors and adding one of their ends to the other one's tip and then making a single vector from them, and that vector is corresponding to the sum of the two complex numbers. Now similar to this, if you consider subtracting one complex number from another, since subtraction is just negative addition, you can think we basically have two vectors. One of them we take and we reverse their direction. So for example, if I take this one and this vector, all I have to do in order to subtract the second vector, which is the vector corresponding to z2, which is this point right here, z2, from z1, is to just reverse it by doing its same direction but opposite side like this, and taking that vector and putting it at the end of the first vector like this. So therefore, if I do z1 minus z2, it's going to be the same thing as z1 plus negative z2, and negative z2 is just going to be this vector right here, or I can draw it over here and write it as this vector right here, and then I can take that vector, add it to the end of the first number, which is z1, and then I will have the final vector corresponding to z1 minus z2. So therefore, the point right here, which can be found by adding this vector, which is the negative z2 vector, to the z1 vector like this, is going to be the point corresponding to z1 minus z2. And of course, we can do it the other way also. We can do z2 minus z1, and in order to do that, all we have to do is to take z1 vector, reverse it, and add it to the tip of the z2 vector. So we can take this thing, reverse its direction, and add it like this, and the point right here is going to be corresponding to z2 minus z1. And that is all we have for the different algebraic operations of addition and subtraction, and also conjugation on this kind of diagram. So now let's consider how we can represent this in a circular function method in order to convert this linear geometry into polar coordinates. So basically, instead of having an x direction and a y direction, we can instead have a radius which is going to be the distance from the origin of a particular point, a particular complex number, and its angle related to some axis, which in this case we're going to use the positive real axis in the anticlockwise direction. And using that, we can see how we can represent any complex number using, instead of a and b like this on a real and imaginary axis, and length, which is going to be the radius r, which is going to be the distance of that point from the origin, which by the way is going to be equal to the modulus of the complex number, and an angle which is going to have a special name. It's going to be called the argument of a given complex number. So let's go and see how we can represent complex numbers using, instead of linear coordinates, angular polar coordinates. So let's consider a random complex number z equals a plus bi. So let's say this complex number right here, which is z equals a plus bi. Now, considering this complex number here, what I'm going to do is to first draw a line from the origin to this complex number. So I'm going to draw it from the origin like this to this complex number. So doing so, we can see this complex number is a certain distance here, which I'm going to call r, away from the origin. Now furthermore, I'm going to draw a vertical straight down from this point down to the real axis. I'm going to draw a vertical down like this. Now, since the real axis is horizontal, the angle here in between these two is going to be 90 degrees. And finally, I'm going to label the angle right here as theta. Now, after labeling all of this, we can see, since the coordinates of the point z are a and b due to the fact that z is equal to a plus bi, we know that the side length here of this triangle on the base is equal to a, and the height of this triangle from this base here all the way up to the point z is going to be equal to b. Now, taking a look at this, we can see, if we consider the geometry that we have, we can find that r times cosine of theta is going to be equal to a. Or if I just say cosine of theta and write that formula, cosine of theta is going to be equal to adjacent divided by hypotenuse, which is going to be a divided by r, which we can then use to get that a is equal to r cosine theta. Now similarly, if we consider sine of theta is going to be opposite divided by hypotenuse, which is going to be equal to b divided by r. So b divided by r, and then rearranging that, we can see b is going to be equal to r sine of theta. Now we can see, using this, we can convert between r and theta and a, and r and theta and b. And if we want to go in the reverse direction, if we knew r, we could also find theta. Now, there's one more thing that we can do here, and that's to consider the Pythagoras' theorem for this triangle right here. We can see, since the triangle is a right angled triangle, we can write that r squared is equal to a squared plus b squared. And since this is the case, and since r is positive, we know that r must be equal to the square root of a squared plus b squared. Now, the square root of a squared plus b squared for a complex number is a special value which we call the modulus of that complex number. So therefore, instead of writing it like this, I could say that r is equal to the modulus of the complex number z. So I can write modulus of z. So therefore, using this, we can directly find the radius of this complex number that we need in order to express the polar coordinates by directly taking the modulus of a given complex number. Or we could just write that is the square root of a squared plus b squared, where a and b are the two numbers that make up the complex number. Z equals a plus bi. Now, for the angle theta here, what we can do is to take these two equations and divide them by each other, and we can see if we divide the second equation by the first, the r's are going to cancel out since r is non-zero here, and we're going to get sine theta divided by cosine theta, which is going to be equal to tan theta, and on the other side we're going to have b divided by a. So therefore this gives us that tan theta is equal to b divided by a. Now tan theta being equal to b divided by a does not actually directly give us the value of theta. This is because there are multiple angles of theta that can give us the same b divided by a. So to find the exact angle theta from the real axis in the anticlockwise direction or clockwise direction that we require in order to find the line corresponding to the point Z, we are going to have to do some geometry. We are going to have to consider the actual physical geometry of the point Z, see if it's in the first quadrant, second quadrant, third quadrant, or fourth quadrant, and then use the geometrical facts that we know in order to find the actual point. But we'll leave that for now separate. We'll just assume that if we know tan of theta being equal to b divided by a, and we know an approximate position of the value of this point right here Z, then we can find the corresponding angle theta. Or in the inverse case, if we know the angle theta and the radius r, then we can of course find a and b, and therefore we can convert in between the linear coordinates and angular coordinates, or the angular coordinates to linear coordinates. So with this system, we can now represent the complex number z equals a plus bi in a different form. If we consider what that form is going to be, we can see all we have to do is to replace a with the value of a in terms of r and theta, and b in terms of the value of b in terms of r and theta. So if we do that, we can see, if I delete this axis right here, we can see a is equal to r times cosine of theta and b is equal to r times sine of theta. If we take this formula and substitute, we can see we're going to get Z equals a plus bi, which is going to be r times cosine of theta plus r times I times sine of theta. Now here, if we factorize out the r, we're going to get r times, and we're going to get on the inside cosine theta plus I sine of theta. And this is the general polar form that we can expect a complex number to be in. Given an angle theta and a radius r, the given complex number relative to that is going to be equal to r times cosine theta plus I sine theta. Now, considering this format, you might note that r is the size of the complex number, and this value here, cosine theta plus I sine theta, is a complex number with unit length. If you consider the modulus of this thing, it's going to be the square root of cosine squared plus sine squared, which is of course going to be equal to 1, and therefore this complex number here has size 1. So if you think about this in terms of vectors, you can think that the complex number here is the unit complex number in the direction of the overall complex number Z, and multiplying it by the magnitude of r. So that is how this format of complex numbers is built up. Now in this, there are two variables that we need. One is the radius r and the other is the angle theta. In this, the radius r is typically called the modulus. We can say r is the modulus and theta is what we call the argument. So theta is the argument. Now, for these two, there are certain rules. For r, we must have r being a positive number. So r must be greater than or equal to 0. Then the only case that we can be equal to 0 is if the point that we are representing is exactly the origin. For any other point, r is greater than 0. So we basically make sure that the radius or the distance from the origin to our point is a positive value. Now after that, considering the argument has a different kind of restriction. So considering these complex numbers, we can see that there are multiple possible different angles that will give you the same exact point. We have theta here, but we also have theta plus 2 pi radians, which is this angle right here. We have theta plus 4 pi, which is this angle right here, and so on and so forth in that direction. But we also have theta minus pi radians, which is the 2 pi radians rather, which is this angle right here. We have theta minus 4 pi radians, which is this angle right here, and so on. So there are an infinite number of angles that will give us this point Z. Now out of those, if we want to select a specific one, we will select one that is somewhere in between positive pi and negative pi radians. That particular one is what we call the principal argument. However, for a complex number, any other angle or the total sum of all possible angles that will give us that given complex number are simply referred to by argument. So here we have two terminologies. One is argument and the other is principal argument. Now, the principal argument is represented by capital ARG. So we can say capital ARG of a given complex number, let's say Z, and that number is the argument which is such that, let's say, theta is in between negative pi and positive pi, but for positive pi we have inclusive. The reason for that is because eventually you will need pi radian angle, because we need negative numbers. Of course, a negative number is basically a number that has no imaginary part but negative real part, and for that we can see the angle from the positive real axis is in fact pi radians. So for that reason, we include positive pi by pi, rather not pi by 2, positive pi, but we don't include negative pi. So therefore, the principal argument is the argument of Z written with a capital A, which is the angle out of all the possible infinite angles that is in between negative pi and pi inclusive. Now, other than this, if we want to just include every single possible angle, we can, instead of writing capital A, write simple ARG Z. Now, simple ARG Z represents not just the principal one, but all possible arguments of Z. So basically every possible angle that we could have, which is all of these angles, theta, theta plus 2 pi, theta plus 4 pi, and all of those angles, and then also theta minus pi, so theta minus 2 pi, theta minus 4 pi, and so on and so forth. All of those angles are represented by simple ARG of Z, but if we want the one angle that's in between negative pi and pi, we get capital ARG of Z. So these are the restrictions placed on r and theta, and given this, we can express any complex number in terms of any r and theta. And if we want to convert that back into linear form, all we have to do is to take a equals r cos theta and b equals r sin theta. And also, as we discussed, if we want to convert any a and b into an r and theta, r is going to be equal to square root of a squared plus b squared, and tan of theta is going to be equal to b divided by a, and we simply need to use the geometrical facts in order to find the actual angle theta corresponding to this. So now we have completed our discussion on what we can do in order to convert a linear point or a point given linearly as z equals a plus bi in the complex plane into polar coordinates. Let's now discuss how this particular form of polar coordinates can be useful when we consider multiplication of two complex numbers and the division of one complex number by another. So to start off, let's suppose that there are two complex numbers z1 and z2 that we want to multiply by each other. So let's suppose we have z1 over here, and let's suppose we have z2 over here. And let's also suppose that z1 has a size of r1. So if I say a line like this, it's going to have a size of r1 and it's going to have an angle here of theta 1. Similarly, let's suppose that the other complex number, which is this number right here, has r2 size and it has an angle of theta 2 again to the real axis. Now given this, we can write, given this format, that z1 is equal to r1 times the cosine of theta 1 plus I sine of theta 1. And similarly, if z2 has length of r2 and angle of theta 2, then we can write that z2 must be equal to r2 times cosine theta 2 plus I sine theta 2. Now, given this, let's try to multiply z1 by z2. So doing so, we can see we're going to have z1 times z2, which if I write in terms of these two right here, we can write z1 times z2 as r1 times the bracket of cosine of theta 1 plus I sine of theta 1 times r2 times the bracket of cosine of theta 2 plus I sine of theta 2. And now what we can do is to take this r1 and r2 to the left hand side like this, r1 times r2 times, and then here we can see this term has two terms on the inside of it, cosine theta 1 and I sine theta 1, And this term also has two terms on the inside, cosine theta 2 times I sine plus I sine theta 2, and therefore if we multiply this term by this term, we are going to get 4 total terms. So if we do that, we can see, considering multiplying these two, the first term we would get is cosine theta 1 times cosine theta 2. So therefore we can write cosine theta 1 times cosine theta 2. The second term we get is cosine theta 1 times I sine theta 2, which I'm going to take the I to the front and write this as plus I cosine theta 1 sine theta 2. The next term we'd get after that is going to be I sine theta 1 times cosine theta 2, which once again I'm going to keep the I at the front and write this as I sine theta 1 cosine theta 2, and the final term we'd get is I sine theta 1 times I sine theta 2, which I'm going to take the two i's and write them as I squared. So I'm going to write plus I squared, and then we have sine theta 1 sine theta 2, and then close bracket. So now let's simplify these 4 terms. So you can see these R1 and R2 are going to remain as is. We're going to have R1 times R2 times, and then if we consider the rest of it, we can see we have an I squared here, and I squared by definition is equal to negative 1. I is defined such that I squared is negative 1. So therefore we have a cosine theta 1 times cosine theta 2 term here, and a minus sine theta 1 sine theta 2 term here. What I'm going to do is to group these two together and write them as cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2. And then to that we're going to add the rest of the terms, which we can see here. We have this term and this term to add. Now in both of these terms, notice that there's an I in them. What I'm going to do is to factorize out the I and write everything else inside of brackets. I'm going to write plus I times, and then on the inside if we remove the i's, we're going to have left cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2, sine theta 1 cosine theta 2, and then close bracket, and then we can close the second bracket. So now we have this. But if you take a look at the expressions that we have here, you'll notice that this term right here is simply the cosine of theta 1 plus theta 2. And if you look at this term right here, you'll notice this term is just the sine of theta 1 plus theta 2. And therefore if we replace that, we can see we're going to get R1 times R2 times, and inside of a bracket we can write this is going to be equal to the cosine of theta 1 plus theta 2 according to the formula, the identity that we know, plus I times, and then the second thing here is going to be sine of theta 1 plus theta 2. Now combining all of this stuff here, we can see we have a given radius here, we have an angle on the inside here, and we can see that same exact angle is represented here. Now let's suppose we use single symbols for each of these. If we do so, we can see R1 times R2 could be written as just R, and then all this stuff here we could write theta 1 plus theta 2 as just another angle theta. So therefore we get the form of R times cosine of theta plus I times the sine of theta, where R is equal to R1 times R2 and theta is equal to theta 1 plus theta 2. So therefore we can see we get another complex number z, let's say, which is of the form R times cosine theta plus I sine theta, which is the standard polar form of a complex number. But we can see the radius of the complex number, which size is R1 times R2, the product of the two sizes of the two complex numbers we multiplied. And the angle specifically is very important because the angle is equal to the sum of the two angles of the numbers that we multiplied. So basically, if you have two complex numbers and you multiply them together, the angle of the resultant complex number is going to be equal to the sum of the two angles of the two original complex numbers. And this makes multiplying complex numbers using polar coordinates very easy and simple. All you have to do is to take their sizes and multiply them together, and then you get the overall size of the final answer. And for the angle, you just add the two angles together, and then you can use a protractor or something or a compass to draw a line in that direction, and then go a distance of R1 times R2 along that line in order to find the respective point. So in this case, let's suppose that R1 times R2 is this length right here, and theta 1 plus theta 2 is this angle right here. Then this point is corresponding to Z1 times Z2. So now similar to this, if you consider division, division also gets a very similar identity, except there's a small difference in that R is not R1 times R2, but rather R1 divided by R2 Theta is not theta 1 plus theta 2, but rather theta 1 minus theta 2, where theta 2 and r2 belong to the complex number that we're dividing by. So if we go down, we can see, if we go down and try it again and consider again two complex numbers, let's say this complex number right here and this one right here, where this is theta 1, this is theta 2, and then this length here is r1, this is r2, meaning that the point here is z1 and this is z2, and then we'll of course have the two identities that we had above, that z1 is equal to r1 times cosine theta 1 plus I sine theta 1, and similarly z2 is equal to r2 times cosine theta 2 plus I sine theta 2. And then given this, what we're going to do now is to consider dividing z1 by z2. So if we do z1 divide by z2 and we substitute what we have here, we can see we're going to get exactly this thing right here. We can actually just copy the exact same thing into here, and then we can draw the vinculum line to indicate division here. So we can have this thing right here. And right now we can see we have r1 divided by r2, which I'm going to take out. But then we can also see we have one complex number divided by another complex number. Now I want to get rid of the complex number on the denominator. To do so, as we know, all you have to do is to multiply this number by its conjugate, which means instead of having cosine theta 2 plus I sine theta 2, I'm going to multiply the top and bottom by cosine theta 2 minus I sine theta 2. So if I multiply the top and bottom by this number, then the denominator is going to have no complex numbers. It's going to have only real numbers. So if I do that, if I do cosine theta 2 minus I sine theta 2 and multiply the top and bottom by this, considering the top, we're going to have r1 divided by r2, which I'm going to leave out, r1 divided by r2, but then we're going to have to multiply these two out, and for the denominator also we're going to have to multiply these two out. Now, if we first do the numerator and consider drawing a big square bracket here and consider each of the terms in the numerator, we can see we have 4 terms, and the first term is going to be cosine theta 1 times cosine theta 2. So therefore we have cosine theta 1 cosine theta 2. Now for the second term is going to be cosine theta 1 times negative I sine theta 2. So I can write negative I cosine theta 1 sine theta 2. And then for the next term, I can write I sine theta 1 times cosine theta 2. So I can write plus I sine theta 1 cosine theta 2. And finally, I can write I sine theta 1 times negative I sine theta 2, which is going to be negative I squared sine theta 1 and sine theta 2. And close bracket. Now for the denominator, if we consider, we're going to have eliminated all of the complex part here, we're going to have only real parts, and considering what we're going to get, since there's a difference of squares, we're going to have cosine theta 2 times cosine theta 2, or cosine square theta 2, cosine square theta 2, and then we're going to have I sine theta 2 times negative I sine theta 2 is going to be minus I squared sine squared theta 2. And the other two terms of course will cancel, since here we have a plus b and a minus b. So now considering this, if we simplify, we can see we have r1 divided by r2 here, and then considering the rest of the expression, there is a minus I squared here and a minus I squared here. Now since I squared is defined to be equal to minus 1, minus I squared would be plus 1. So therefore what we have here is plus 1, and what we have here is also plus 1. Now considering that in the top, I'm once again going to do the same thing that I did for the multiplication case. I'm going to take this I sine theta 1 times sine theta 2 component and bring it right next to the cosine theta times cosine theta component. So doing so, the bracket turns into cosine theta 1 cosine theta 2, and then we're going to have plus sine theta 1 sine theta 2, and I'm going to put this inside of another bracket. And then for the other bracket, I'm going to take these two terms, take the I out of them and write plus I times, and then considering these two, I'm going to take the minus term, put it at the end, take the plus term, put it at the front, and write this as being equal to sine theta 1 cosine theta 2 minus cosine theta 1 sine theta 2. And now close bracket, and then close the second bracket. Now for the denominator, we can see if minus I squared is equal to plus 1, then we have cosine squared theta 2 plus sine squared theta 2. Now as we know from the identity, if you have any cosine squared plus sine squared of any given angle is going to be equal to 1. So therefore this term right here is just 1. We can ignore it and only consider the rest of the equation. Now considering the rest of it, we can see we have r1 divided by r2 multiplied by all of this stuff here, and considering the stuff we have cosine theta 1 times cosine theta 2 plus sine theta 1 times sine theta 2. And as we know, that right there is the equation for the cosine of theta 1 minus theta 2. It's also the equation for cosine of theta 2 minus theta 1, but for now I'm going to write as cosine of theta 1 minus theta 2. And the reason for that is, if you consider the second term, which is I times something, the something that we have on the inside here is the sine of theta 1 minus theta 2, not theta 2 minus theta 1. This one can only be theta 1 minus theta 2. So therefore we can see we have sine of theta 1 minus theta 2. Now considering the expression that we have here, we can see we have some radius times cosine of some angle plus I sine of that same angle. We can see that means this is of the form r times cosine theta plus I sine theta. Now considering the values of r and theta here, we can see where r is equal to r1 divided by r2, and we can also see theta is equal to theta 1 minus theta 2. So we can see, similar to multiplication, we have an ident for division. For multiplication, we had the total radius r being equal to r1 times r2 and the total angle being equal to theta 1 plus theta 2. But down here we can see the total radius we get is r1 divided by r2, where r1 is the radius of the number on top and r2 is the radius of the number on bottom, and the angle theta is theta 1 minus theta 2, where theta 1 is the angle of the number on top and theta 2 is the angle of the number on bottom. So therefore, we can again, similar to how we did multiplication, very easily find one number z1 divided by another number z2 in the complex plane. All we need to do is to find their radii, divide the radius of the thing on top by the radius of the thing on bottom, and then draw a circle at that radius. Or instead, we could find the angle first and then take the angle of the thing on top, subtract the angle of the thing on bottom, and then draw a line in that direction, go a distance of r1 divided by r2 along that line and mark the point, and that point would be the point corresponding to z1 divided by z2. So we can see that this polar method makes multiplication and division of complex numbers very easy, because all you have to do is to multiply or divide the radiuses corresponding, and then to find the exact point, we just have to either add or subtract the angles. If we are multiplying, we add the angles. If we are dividing, we subtract the angles. And that is all we're going to be doing in this video regarding multiplying and dividing complex numbers with polar coordinates. So now finally, let's end the video with a summary of what we've learned so far. So at the start of the video, we introduced the Argand diagram. This is a method where you can denote any complex number by its real part and imaginary part on a two-dimensional plot where we have two orthogonal axes, the real axis and the imaginary axis. On the real axis, you mark the part A of a complex number in the form z equals a plus bi, and on the imaginary axis, you don't mark b times I. Instead, you just mark the value b on the imaginary axis corresponding to the imaginary part of the complex number z. Now after this, we then discussed how you can mark different complex numbers. We did a couple of examples, and then we discussed some transformations that you can do to complex numbers and how they look on this geometrical representation. We talked about what happens when you do lambda times z on an Argand diagram, and how if lambda is greater than 1, you're going to get some number that's on this part of the line. If lambda is in between 0 and 1, you're going to get some number on this part of the line. And then if lambda is in between -1 and 0, you're going to get a number on this part of the line. And finally, if lambda is a number less than -1, you're going to get a number on this part of the line. After that, we then discussed what happens when you take the conjugate and how that looks geometrically on the Argand diagram. We showed how you have to just mirror the number across the real axis in order to get its conjugate. Now after this, we then talked about how you can add or subtract complex numbers and how it looks on the complex plane. We also talked about how, if you think about these complex numbers as vectors from the origin, it will make it much simpler to understand how adding or subtracting one complex number from another works. Now after this, we then discussed how you can convert this linear format of real part and imaginary part of a complex number into a polar coordinate system where you have the radius of the complex number, which is the distance of the complex number from the origin, and the angle theta, which is called the argument, which is the angle from the real axis in the anticlockwise direction of that complex number. We also talked about the fact that if you go in the clockwise direction instead, it's going to be negative. Now after this, we talked about the limitations of r and theta. R is called the modulus of a complex number and it must be a positive value, it cannot be negative. And given this, theta is what we call the argument, and we talked about how there are multiple different possible infinite number of, in fact, arguments that a given complex number could have, but out of them, capital ARG of a complex number represents the principal argument, which is the argument that is in between negative pi and pi inclusive. And then we talked about how if you instead use simple ARG can represent all the possible arguments of a given complex number. Now after this, we then showed how multiplying and dividing complex numbers works when you have the polar form of r times cosine theta plus I sine theta. First we take a look at multiplying two complex numbers, and we noted that when you multiply two complex numbers, the result basically looks like r times cosine theta plus I sine theta, where r is the total radius of the complex number, which is the product of the two individual radii of the two complex numbers that you multiply together, and theta is the sum of the two angles of the two original complex numbers that you started with. Now after this, we then consider dividing two complex numbers, and so that if you divide one complex number z1 by another complex number z2, then the resultant is of the form r times cosine theta plus I sine theta, where r is equal to r1 divided by r2, where r1 is the radius of the complex number on the numerator and r2 is the radius of the complex number on the numerator. And then the angle theta is equal to theta 1 minus theta 2, where theta 1 is the angle of the complex number on the numerator and theta 2, the angle that is subtracted, is the angle of the complex number on the denominator. And with that, we have finished this video. So I hope you enjoyed. If you have any feedback, post it in the comments down below. You can check out the next video with this link in the top right here. Thank you for watching and goodbye.